Good day everyone. So this is my final exam output in BSED Math 8 Modern Geometry. So I will first discuss the characteristic postulate of elliptic geometry. So this is the postulate. Any two lines in a plane meet at an ordinary point. So we have here figure 9.32. If figure 9.32 is in elliptic geometry, with EH, we have here line EH in the figure and line FI are both perpendicular to the line segment CG. These two lines meet at some point at A because of the characteristic postulate at any two lines intersect. So this line, so EH and FI, if you extend that, they will meet at point A. In elliptic geometry, it is customary, or it is, let's say, normal to use curves to show straight lines. So if DE, line DE, is congruent to line EF, then triangle AEF is congruent to triangle AEB. Why? Using the SAS postulate, side angle side, we have here the right angles. We have the DE and EF as congruent. So first side BE is congruent to line EF. Then the right angles, definition of right angles, all right angles are congruent. Then AE with reflectivity, AE is congruent to itself. So SAS, side angle side, excuse me. And AD, so this line AD is also perpendicular to CG. So AD is perpendicular to CG. By an extension of this argument, it can be shown that every line through A intersects line segment AG at right angles. So all the points that passes through A or from A intersect the line segment CG. So it can be extended passing through the line segment CG, and it creates right angles because they are perpendicular to that line. So point A is called pole of line segment CG, and line segment CG is polar for point A. So this point A is the pole while CG is the polar. Here, the distance from A to any point on CG is a constant. In figure 9.32, if line AE, so we have here line AE in the figure, is congruent to line EB, then BEF, triangle BEF, is congruent to triangle AEF. So these two triangles are congruent. How? Again, we use the SAS postulate, side angle side. So we are given there AE is congruent to EB. Since they are congruent and AE is perpendicular to CG, then it creates right angle. So BEF is also a right angle. Thus, AE is congruent to EB, and right angles, definition of right angles, all right angles are congruent. Then, we have EF with reflectivity again. EF is congruent to itself. Thus, we can use SAS postulate to prove that AEF and BEF are congruent. And we can also see there that AFB are collinear because they lie on the same line. This means that B is also a pole of CG. It is opposite to A and also a pole of CG, where CG is also a polar of B. And that two lines intersect in 2 points. It is it is also possible to consider them as identical in single elliptic geometry. The common polar of the two points of intersection is the unique common perpendicular to the two lines. Interestingly enough, two straight lines such as ADB, the line ADB, and AFB enclose a region in elliptic geometry. So they have a region here. This region is called the digon or biangle. It has two angles. Okay. So fortunately, the elliptic geometry of the plane can be explained conveniently by comparison with a familiar model, so the Earth, and the lines there are the longitude of its surface. In figure 9.32, think of pole A and pole B as the north and south poles, while line segment CG as the equator. So that is the characteristic postulate of elliptic geometry. Now let's go to theorem 3.7.1. Excuse me. The segment joining the midpoint of the base and summit of a Saccheri quadrilateral is perpendicular to both the base and the summit. So here's the proof. Given the Saccheri quadrilateral ABCD with right angles BAD, so we have a right angle here, BAD, and ABC. Further assume that E and F, so E and F are the midpoints of AB and CD. So E is the midpoint of AB and F is the midpoint of CD. Now AE, since midpoint, we can say that AE is congruent to EB. Line AE is congruent to line EB, and DF is congruent to line FC. Now we can say that DAE, triangle DAE, is congruent to triangle CBE, with SAS postulate such that line DA is congruent to line CB, angle DAE is congruent to angle CBA, which are right angles, and the definition of right angles, all right angles are congruent, and AE, the line AE, is congruent to line EB because of the definition of midpoint, which in two opposite lines are equidistant. Since the two triangles are congruent, then DE, line DE here, and line CE are congruent with CPCTC, or corresponding parts of congruent triangles are congruent. Now by SSS postulate, side postulate, the triangle DFE is congruent to the triangle CFE, as we can see there. Why? DF is congruent, line DF is congruent to line FC, with midpoint, definition of midpoint, opposite lines are equidistant. Then DE, line DE and is congruent to line CE because of CPCTC again, corresponding parts of congruent triangles are congruent, and FE is congruent to itself by reflectivity. So by the definition of perpendicular lines, AB is perpendicular to EF. Line AB is perpendicular to line EF. Therefore, line EF is perpendicular to both line AB and line CD. Now, theorem 3.7.2. The summit angles of a Saccheri quadrilateral are congruent and obtuse. So here's the proof. We have here figure 9.34. In the figure 9.34, let ABCD be any Saccheri quadrilateral with O and O prime as the poles of line segment EF. So we have here the line segment EF. So the line joining the midpoints of the base and the summit. So this line EF, line segment EF, is the line segment that joins the base and the summit. So that the summit angles are congruent, comes from the congruent triangles mentioned in the proof of theorem 3.7.1. So to show that the summit angles are obtuse, so let's show that the summit angles are obtuse. It can first be established that their supplements are acute. If, as in the figure, X lies on BO prime, line BO prime, if you extend line BO prime, you can have X here. And is the pole, so X is the pole of line segment BC. So this is a polar of X. Then BX, we have line BX is greater than line BO prime. So we can see there in the figure that line BX is greater than line BO prime. Since BO prime is less than EO prime, we can see there that EO prime is greater than BO prime. Thus, BCD, angle BCD is obtuse. So that is the proof of theorem 3.7.2. Now let's go to theorem 9.20, which is in elliptic geometry, a Lambert quadrilateral has its fourth angle obtuse, and each side of this angle is shorter than the side opposite. So here's the proof. Lambert quadrilateral is formed using the half of Saccheri quadrilateral from the line segment. So if we go back to the figure in the theorem 3.7.1, so the half there is FECB, FEBC. So the midpoints of the base and summit to the other side of the quadrilateral. So FE is the midpoint, the line joining the base and the summit. Then the other side is this BC. So looking back at the theorem 3.7.1 and theorem 3.7.2, we can prove that the fourth angle of the Lambert quadrilateral is an obtuse angle. So here. Now let's go to theorem 9.21. States that the sum of the measures of the angles of any triangle is greater than pi. So here's the proof. In connection from theorem 3.7.1 and theorem 3.7.2, from the Saccheri and the Lambert quadrilateral, knowing that on the fourth angle is obtuse, since in the Euclidean geometry, any normal triangle sums up to a pi. In the non-Euclidean geometry, any triangle in elliptic geometry is greater than a pi. Therefore, the sum of the measures of the angles of any triangle is greater than pi. So that's the proof in 9.21. Now let's go to the last theorem, which is 9.22. The sum of the measures of the angles of any quadrilateral is greater than 2 pi. So here's the proof. In this theorem, any quadrilateral can be seen as greater than 2 pi with theorem 3.7.1 and theorem 3.7.2, such that angle FDA is congruent to angle FCB. Since in theorem 3.7.1 and 3.7.2 proves that they are congruent and obtuse, so FDA and FCB are congruent and also obtuse. Normally, in a quadrilateral sums up to 2 pi in Euclidean geometry. But since there are one or two obtuse angles in a quadrilateral of elliptic geometry, so if using Saccheri quadrilateral, there are two obtuse angles. But if you use Lambert quadrilateral, this side only, you can have one obtuse angle. So but since there are one or two obtuse angles in a quadrilateral of elliptic geometry, then it sums up more than 2 pi. So it sums up because this is a right angle, this is a right angle, then obtuse, then it sums up more than 2 pi or more than 360 degrees. Therefore, the sum of the measures of the angles of any quadrilateral is greater than 2 pi. That's all, and thank you.